Hello, my name is Kai Takeuchi, and this is Physics 2211 Lab 5. For the introduction, the purpose of this lab is to analyze the motion of a falling slinky and create a model for this motion. To do this, I use Tracker to place the markers to track the falling motion of the bottom of the slinky. I then use GlowScript to code the modeled motion, and the slinky first compressed, with the bottom staying in the same place until the slinky fully relaxed and then fell. The slinky then quickly accelerated to its terminal velocity, which is the rate it fell at until hitting the ground. Here are the physics principles used in this lab. First, Newton's second law, change in momentum, is directly related to net force. As you can see, F net equals delta P over delta T, uh, which can then be manipulated into other formulas used. The drag force is the force caused by the air resisting the motion of the object, where B is proportionally constant, V is the speed, and V hat is the direction of the velocity. And finally, the gravitational force, which is the slinky force, is equal to this. As you can see, F of G equals negative mg j hat, and F slinky equals F perpendicular, which also equals mg j hat, which is the opposite of force of gravity. Here's the experiment. The video on the right is where I plugged in all the tracker things to get data from. The observed motion was the mass was 0.218 kilograms. The reference height was 1.75 meters. The initial position was 3.778 e negative 3, negative 4.951 e negative 3, and 0 meters. And there was no initial velocity. The position came from where I set the tracker to start. Here's the GlowScript code I used. For the initial conditions, I manipulated the ball.m to be the initial mass for the slinky. And then I changed the initial position and velocity to match what I got from tracker. And then I also set the drag proportionality constant at the bottom. For GlowScript, the second part was the slinky compressing. First, I manipulated the time while the slinky's position is constant, and then the gravitational force and slinky force in the middle there, and then use the position update formula to get a new position of the slinky. Finally, the last part was the slinky falling. Here I changed the while loop to be the time until the slinky hits the ground, and then plugged in the gravitational and drag forces, and then once again used the position update and velocity update to get my final values. Here is the result of the experiment, the modeled versus the observed position. As you can see on the right, very similar to one another. And for the what if, what would happen if a large mass was attached to the end of the slinky? This would depend on the K value of slinky to pull it back up. If the mass of the weight were too heavy for the spring force to keep it in place, it would fall. And if it were not strong enough to keep it in place, then if it were strong enough to keep it in place, then it would stay as is. Thank you.